This is the first lesson on chapter 4, and we begin with derivatives and graphs. Basically, we want to find out how the derivative is shaping up the graph, how the derivative is affecting the graph. We can summarize these kind of like these. First, let's look at the sign of the first derivatives and then increasing, decreasing nature of the original function. Here, when the derivative is positive, then the original function must increase. We're talking about this kind of behavior here. As you can see, we have an increasing function. Function is going up. And let's pay particular attention to the tangent line. The red bar is a part of the tangent line for different points. And please note that they're all positive. So positive derivative means the tangent line is pointed upward, and consequently that is driving the original function upward. Increasing comes from the positive derivative. Likewise, if the derivative is negative, you can expect decreasing. And here we go. We have decreasing. This curve is decreasing. And then if you look at the slope of the tangent line, slope of this red bar, they're all pointed downward. They're all negative. So negative derivative gives you decreasing. What if the derivative is 0? Of course, that's going to be neither increasing nor decreasing. This kind of situation. Local minimum here. So decreasing, but hit local minimum and keep on now increasing. That's where we have horizontal tangent, so derivative is 0. Local maximum is another situation. Going up and hit the maximum and coming down. And then we have horizontal tangent like this. But neither increasing nor decreasing, neither maximum nor the minimum. This can happen. Just graph goes up and keep going up. Or in some cases, the derivative does not exist at all. All those kind of things are called the critical points. Derivative is 0 or derivative doesn't exist. And one conclusion you can deduce is if you're going to have local extreme points, local maximum or local minimum, it had better be a critical points. If you select a point like this, keep on increasing, that's not going to be local maximum or local minimum. However, not vice versa. We can have this kind of situation. Derivative is 0, it's a critical point, but neither maximum nor minimum. Of course, if you have a cusp, you can have really various situations. Now let's talk a little bit more about critical points. And we say f has a critical point at x equal to c, or the critical point c comma f of c, when the derivative doesn't exist, or the derivative is 0. As you can see, local maximum or local minimum are two possibilities of critical points, and this one is local minimum too, by the way. But it is possible that neither maximum, neither minimum. And how is local minimum, local maximum being affected by the derivative? Local maximum is of course occurring when f goes up, hit maximum, and f goes down, kind of like this, go up, hit maximum, and comes down. And that's related to the sign of the derivative. The derivative must be positive to go up and hit horizontal tangent, and derivative must be negative from that point on. So if you have the derivative function and if you see a sign change, you're going to get a local maximum kind of like that, or local minimum too if it is vice versa. Let me show you. Here's the situation for local minimum, and then decreasing hits minimum and increasing in terms of derivative, negative derivative, and hit horizontal tangent, and then positive derivative. And then of course we can have something like this. Excuse me, a little typo here. The derivative is staying positive or staying negative, kind of like this. Stay positive, so increasing and keep on increasing, or stay negative, decreasing and keep on decreasing. And of course we'll have derivative 0 right here and there. In that case, no extremum. So these are neither maximum and nor minimum case. Let's postpone the other topics and let's go over to a problem. Let's consider a motivational problem and let's check out how graphs are being affected by the derivative. Here's a problem. Answer the following questions regarding the original function f of x, which highlighted in red, while the graph of this derivative function f prime of x is given below. The derivative is blue, so the function we are looking at is a derivative function. All the questions here will be about the original function, which I did not give you. So if you say, well, we have local maximum at 1.5 comma about 3 or 3.1, or local minimum at 3 comma 0, local minimum at -1 comma -1 and 1.2 or something, you're gonna get 0 credit right away, because that's when the derivative function has local maximum, minimum, or increasing, decreasing, not the original function. How do we answer the question about original functions increase and decrease? How do we answer questions about original functions critical points? In particular, I'm interested in part A and part B, and this diagram will give you the full solution here. Let's see. Let me move this diagram right below this graph and let's discuss this. Let's look at the derivative function, which we see here. The original function is not given, but I can deduce its behavior from the sign of the derivative function. Let's find out the critical points where the derivative hits 0. At x equal to -3 right here, the derivative function hit 0. Y coordinate is becoming 0 right here. At x equal to 0, the derivative function hits 0. And x equal to 3, the derivative function hits 0. Those 3 points are highlighted in this number line. And then what? Let's find out the sign of the derivative function. Less than -3, so this part of the graph where my mouse is, the graph of the derivative function is above the x-axis, which means the derivative is positive here. Less than -3, positive derivative. Now, between -3 and 0, the derivative function, which we are seeing, is below the x-axis. That means the derivative is negative between -3 and 0. So I have this diagram here, negative. Now, between 0 and 3, this part, the derivative is positive. The graph is above the x-axis. So we have positive sign. And finally, when x is greater than 3, so this part of the graph here, again, graph is above the x-axis. The derivative function is positive here. So by looking at the crossing or touching points, we got the critical points, -3, 0, and 3. Only the x coordinates matter. And then let's look at the sign of the first derivative function by looking at this location above the x-axis versus below the x-axis. That's how we found out plus, minus, plus, and plus. Finally, let us deduce the behavior of the original function. When the derivative is positive, original function must be increasing, so let's use this arrow to denote it's increasing. And then when the derivative is negative, original function must be decreasing. Now, between 0 and 3, we saw that derivative is positive, right? Above the x-axis. So original function is increasing, going up. And after 3, derivative is still positive, so original function must be keep on increasing. We have something like this. Increasing here, now decreasing, increasing, and keep on increasing. So change here, increasing to decreasing, gave us local maximum here. And this change, decreasing and then increasing, gave me local minimum. And then increasing and then keep on increasing, neither maximum nor minimum. So this diagram completely answered part A and part B. There's no computation involved, no formula, no room to make any silly algebraic mistake here. So everybody who really studied this one can cash in this kind of problem, and everybody who did not study hard will get creamed in this kind of problems. That has been my experience. Let me emphasize again. What is the order of the problem? A and B. A is talking about increasing, decreasing nature. B is about critical points, but these two problems are connected. First, we find out x-coordinate of the critical points, or critical numbers, they say. Crossing the x-axis at x equal to -3, x equal to 0, and touching at x equals to 3. Those are three critical points of the original function. And then those 3 points, 3 x-coordinates, divide the number line in 4 pieces. Those 3 divide the number line in 4 pieces. 1, 2, 3, and 4. So less than -3, the graph of the derivative is above the x-axis. Consequently, the original function is increasing. Between -3 and 0, the derivative function is below the x-axis. So the original function is decreasing. Now, between 0 and 3, the derivative function is positive, as you can see. So the original function is increasing. Finally, when x is greater than 3, derivative is still positive after hitting 0. So the original function must be keep on increasing. I think I have picture here. Yes, the red is the original function. And then let me see, let me get this picture back again with this answer key, and let's check. Original function is increasing and hits -3, decreasing and then hits 0, local minimum, and increasing up until x equal to 3 and keep on increasing. Now, it is impossible to find out the y-coordinate value, because if you take the derivative of any constant, that's going to become 0. So if I simply take this red curve and then add 1 or add 17 or subtract 100, we'll have the same result. Therefore, do not try to say anything about y-coordinate value, or you're gonna lose some credit, because that's one way to see that I can see the students did not have complete understanding. Keep only the x-coordinate for this kind of problem. If algebraic equation is given, then you can find out y-coordinate, but I did not give you algebraic equation here. All you can see are x-coordinate values, and they can be answered by this diagram completely. So diagram method, and then plus going up, minus coming down, sign change from plus to minus give you local maximum, sign change from minus plus give local minimum, no sign change keep on increasing or sometimes keep on decreasing, those are gonna be neither. The summary version can be found in this table here. Derivative is positive, original function goes up. Derivative is negative, then original function comes down. Derivative is 0, that's where we have critical points, various situation, local maximum, local minimum, or neither. Positive derivative, increasing. Negative derivative, decreasing. Zero derivative, critical points. This table here.